Okay. Hey y'all, to my adoring fan club and everything. We are, as the kids say, so back. So we're gonna be going through this horse race assignment. We've got new tech, we've got a screen recording now, and also what I thought calculus really needed, honestly, was more of my face. So we've got that in there. We're just gonna go through this Desmos assignment until everyone understands it, or until my eyeballs fall out. But we're gonna start with the most basic thing that we've got here, which is just writing our y in terms of x. So, and I'm hoping this thing is recording right here. We've got these two equations. X is equal to square root t, and then y is equal to 3t squared plus 2t. So, essentially, we just want to use basic algebra and we're going to substitute. We're going to try to figure out what t is. We're going to figure out what t is from here, and then we're just going to plug it in here and here. So in this case, I notice if I square both sides of this equation, then I get x squared is equal to t. So now I can rewrite this equation as y is equal to 3 x squared plus 2 x squared. We're just doing basic substitution here. And then we can rewrite with exponent rules, and we can officially type this into our equation. Let's see. 3x to the fourth plus 2x squared. Wow. Guys, we've succeeded at doing basic algebra, and I'm double checking again that you can read what I can do. But let's go on to the next one. This is going to be the same deal. We're just going to kind of speed run through these. We have x is equal to ln of t, y is equal to t squared plus t. We realize if we put e to the power of both sides equals e to the power of ln t, then we get e to the x is equal to t. So we're going to substitute that again. Y is equal to, let's see, e to the power of x squared plus e to the power of x. We're going to simplify that again. And we're going to try to write this down. When they just say eliminate the parameter, this is all they want you to do. They just want you to substitute it in so it's only in terms of x and y. And we've got good work, once again. Algebraic Higgs. Now, this is where the only thing with eliminate the parameter that might cause a little bit of difficulty, because we don't want to get into the whole complicated world of using arcsine or arc cosine or anything like that, because that just introduces a whole pain into the thing. But what we do know is we have this equation that we learned all in our freshman year, or maybe later, which is sine squared of t plus cosine squared of t is equal to 1. So what we are going to try to do, instead of going through the whole arc cosine and arcsine approach, is we're going to find what sine of t, we're going to isolate sine of t on one side of the equation, we're going to isolate cosine of t on the other side of the equation, and then we're going to set the whole thing equal to 1 after we plug into this equation here. So let's see this in practice. We've got x equals 3 sine of t plus 2, and then we've got y is equal to 4 cosine of t minus 1. So we're going to go to these in order. So let's see, we can subtract 2 from both sides, and we get x minus 2 equals 3 sine of t. And then we can divide both sides by 3, and what we get is x minus 2 divided by 3 is equal to sine of t. And if you don't get that, go ask ChatGPT how to do algebra. We'll be okay. In the meantime, I'm just going to do the same process over here, over 4 is equal to cosine of t. So super great, we figured out what cosine of t and what sine of t are. Now we are just going to plug this into the thing. So, for instead of sine squared or sine of t squared, remember we can rewrite it either way, we're going to write down x minus 2 over 3 squared. Because remember, this is sine squared. Plus what we got for cosine over here, y plus 1 over 4 squared. And remember, that's the same thing as cosine squared of t, because we just isolated. So now we know that sine squared of anything plus cosine squared of anything, as long as they're the same variable, that's going to be equal to 1. And we can just write that as our equation. So we're going to look through these, and we're going to hope and pray that I've done this correctly. Let's see. I think it should be this one. Excellent. Super great. The only thing you'll notice that they've done is they've went ahead and simplified the denominators, because remember we can do that, basic exponent rules. So we have x minus 2 squared over 3 squared, for example, for that first term. And they simplified that into x minus 2 squared over 9. But we should know how to do that, hopefully. Or you know what, maybe not. Maybe whatever floats your boat. So we're going to move on to the next problems, where we're actually going to be doing a tiny bit of calculus. So dy over dx, which is the slope of the overall equation. So in order to do this, what we're going to do is we're going to derive both the equations for x and the equations for y. Because what dy over dx, that's the overall slope that we're looking for. It ends up being, and I'm going to draw a line, by the way, to isolate all the work that we did on problem 1a. dy over dx is the same thing as our rate of change with regards to y over our rate of change with regards to dx. Hopefully you can see here that if we take this right here, if we divide the two by each other, then these two dt's are going to kind of cancel out, because we can just multiply both by dt. But basically this is going to be our formula. It works out to be super simple. So let's give an example. They give us with number 2, y is equal to 3t squared plus 2t, and x is equal to square root t, which I'm going to rewrite here as t to the power of 1 over 2. So we're going to take the derivative, dy over dt, right? We're going to derive it with respect to t, so we're just going to do basic power rule here. So we're going to take this down, multiply it. We're going to get 6t for our first term. We're going to multiply this. We're going to get 2 as our second term, power rule. Ask ChatGPT again. So we're going to move on to this here, though. We're okay with this. This is dx over dt, and we're going to do power rule. 1, and we're going to get 1/2, our coefficient, times t to the power of negative 1/2, which you can also rewrite right here as 1 over 2 square root t. And this should look pretty familiar to you, even if you're used to doing it with x's instead of t's. So we got this term and this term. Now we're just going to divide them by each other. And again, hopefully this makes sense. Your rate of change, let's see, how far you're moving in the y direction, your speed in the y direction, and then your speed in the x direction. If you divide y by x, that should equal slope. So we're going to take this whole 6t plus 2. And this is why we hate the variable t, because it looks just like a plus sign if you have terrible batshit handwriting like I do. So we're going to divide this by 1 over 2 square root t. And I want to get this term at the bottom over to the top, so I'm just going to multiply both the numerator and the denominator by 2 square root t. 2 square root t, which I wrote weirdly at the top there for some reason. And I'm going to do us all the favor of algebraing this out. This ends up being 6t to the power of 3 over 2 plus 4t, or to the power of 1/2, which you could also rewrite as 6t times square root, oh, my bad, 12. You could also rewrite that as 12t times square root t plus 4 square root t, and hopefully you see how we got from point A to point B. So let's type this in. Oh, I guess I already did this one. Sorry guys, I spoiled it for everyone. It's really disappointing of me, I know. But here's our answer. It all works out super nicely. Okay, another question that I spoiled. Guys, I'm so sorry. We're gonna move into our next problem. They give us x, they give us y. We're gonna start with y first. Y is equal to t squared plus t. X is equal to ln of t, and we're just going to do the super simple thing of, again, deriving both of those. So dy over dt, we're going to take a super quick derivative and get 2t plus 1. Here we're going to take a super quick derivative, and we're going to get 1 over t, because we know how log derivatives work. Yay! So we'll divide this term by this term. We'll get 2, I'll write over here, we'll get 2t plus 1 divided by 1 over t, and even though this looks kind of ugly, you're going to multiply the numerator and the denominator by t, and you are going to get this term 2t squared plus t is equal to the overall rate of change. Now, we see why t is the worst variable again? It's okay, we're going to check past self. Did we get this? Woo, we did. We're so proud of past joy. So with that being said, we can move on to this. And our next problem is going to be the exact same thing. Like, even though we have technically a little bit of trigonometry in here, that trigonometry isn't going to be anything we actually have trouble with. We hope, at least. So let's write out what we got again. Y is equal to 4 cosine of t minus 1. And x is equal to 3 sine of t plus 2. So let's just do those simple derivatives. dy over dt, our derivative of y with respect to this variable t here, is just going, we're just going to take the derivative of cosine, which is negative sine. It's going to be negative 4 sine of t. And then over here, when we're deriving x, we're just going to take that simple rule of the derivative of sine is cosine. We're going to carry through the coefficient. Oh, and remember when you're taking the derivative, we don't care about these constants that we have on the end. We're just going to ignore those. So then we're going to take these, divide dy over dx. We're going to get negative 4 sine t over 3 cosine t. And if you're super smart and super amazing, super hot genius, like I clearly am, then we're going to recognize that sine over cosine is equal to tangent. SOHCAHTOA, guys. So let's check if we got this one right, because this wasn't spoiled for us this time. And we're doing excellent. And we even got an emoji in there too. Let's move on to 3a. 3a is going to be a tiny bit annoying, but it's really not that bad once we get into it. What we're going to use is this formula for the second derivative, right? Which is going to be, and I'm going to write it in a little box over here, d over dt of dy over dx over dx over dt is equal to our second derivative. And this makes a lot more sense if you go into Google and you find some like Stack Exchange forum and you look into why we use this notation when we're writing out the second derivative. Then it starts to make more sense why we do it like this, but I'm not going to explain that whole thing right now. So in the meantime, you're just going to have to take my word for it. This is the formula we use. Again, just go into Stack Exchange and find people smarter than me if you want to kind of see the reasoning for why this is the formula or why this works out. You could also kind of solve it algebraically if you really want to know, but not gonna get into all that. Basically, we're just going to use this formula again, and let's try this with the first one. Remember over in part 2a, which I just skipped, we found out that dy over dx, this part right here, y over dx is equal to 12t to the power of 3 over 2 plus 4t to the power of 1 over 2. So we're going to take that, and we're going to take the derivative of that to get this d over dt of dy over dx. So it looks really complicated, but again, it just means we take the derivative of our slope. So we're going to use some basic exponent rules, and we should, if I'm doing my mental math right, actually I'm not going to trust that, we should get 18 times t to the power of 1/2 plus, let's see, 2 times t to the power of negative 1/2. So that is going to be our numerator when we put it into this equation over here. Again, it's a really ugly thing, but something that's super helpful for this bottom part is that we can really just reuse what we did previously. So if we look way back at our work, we found that the derivative of x, let's see, where did we do this problem here? Oh, yeah, we found that dx over dt, when we did that before, was equal to 1 over t. So we're just, okay, we've just skipped forward in time 30 seconds because I circled the wrong number on my worksheet. It made me very confused. But what I was just saying is that we've got our numerator right here, which we've already worked out, and then what our denominator is going to be, which will actually be super helpful if we can do correctly, is just the derivative of x, which we figured out up here and not down here. Don't just circle things because you see them on the paper. So we'll get this numerator again, which I'm going to rewrite for my third time now. 18 t to the power of 1/2, which we've done just fine, plus 2t to the power of negative 1/2. And we're going to divide that by, again, what we previously figured out was the derivative of x equals square root of t. That's going to be 1 over 2 t to the power of 1/2. Now, I'm going to do us all a super great job of mathing this out in my head. You should probably pause here and, do the algebra if you have any academic integrity, and then you should compare the answers that we got. But I'm not a cop. I'm not telling you what to do. So in the meantime, I'm going to mental math this. You're going to get 36t plus 4. Good work, everyone. Only a very slight detour there that we are going to choose not to talk about. Oh, and in the meantime, I'm going to just put some little ducks next to the equations that we care about today. Just so you got that covered. Let's move on to 3c. I'm kind of going to glaze over 3c because we already figured out, alright, we figured out that the derivative, dy over dx, is negative 4/3 tangent of t. It tells us in the delta math problem to just find the coefficient, but this is an easy enough problem. I'm just going to solve out the whole thing for us. So we're going to take the derivative of the top to get our numerator, and then we're going to use the dx over dt that we figured out before as our denominator. Remember, that was from before. That is 3 cosine of t. So our numerator and our denominator, let's figure out what the numerator is first. This is a really simple trig derivative. If you remember your trig derivatives correctly, it's going to be negative 4 over 3, and then the derivative of tangent is secant squared of t. Our denominator, we're just going to carry that through, is 3 cosine of t. And we can simplify this out, because remember, 1 over cosine is secant, or we can rewrite this. Either way that you write this, what this maths out to be is negative 4 over 9 times secant cubed of t. So let's see if we're able to effectively write this coefficient. Let's see, negative 4 over 9 is what you write in delta math if you are stupid and you don't read the explanation that's supposed to be in decimal form. So instead, you're going to do what smart people do, and you're going to learn from Joy and Tanushri's super genius moments, and you're going to see that negative 0.444, or this whole answer of negative 4 over 9 secant t cubed, or what we got. Yay! Now you're saying, wow, Joy, this is so exciting. I'm so glad that I finally feel confident in my ability to take the second derivative of a parametric equation. And now, to that, we are going to have to talk about horizontal and vertical tangents. Horizontal and vertical tangent, actually, I think is arguably easier to do on this kind of equation, though, than it is to do in our regular functions that just have x and y. I think it's easier to do when you have t. Remember, our horizontal tangent, right, is going to be where our slope is 0. It's going to be where, let's see, horizontal tangent, we're going like this. We're strictly a horizontal line, right? That means there's no change in y. We're not going up or down, we're just going strictly horizontal. On the other hand, when we're talking about a vertical tangent, that's where the slope is going to be, well, the slope's going to be undefined. But there's no change in x because we're just going strictly up and down, right? We don't have any kind of change that's horizontally, we're just going vertically. So for a vertical tangent line, right? So another way we can write those two things in this little table that we're making here, another way that we can write those out in math is going to be that our dy over dt, or a change in y, is equal to 0, and our dx over dt is equal to 0. dy is 0 at a horizontal tangent, dx is 0 at a vertical tangent. And now that we've got a super cool equation, we're going to put a duck on it, and we're also going to try to solve this for this lovely equation that we got given today. So, the cool thing about this is you really only need one half of the equation at this point, you know? So our slope of y, we're going to solve that. Okay, they give us our y here. Y equals t squared minus 4t. We can super quickly find that derivative. dt is equal to 2t minus 4, right? And we're just going to find what value of t makes that slope into 0, okay? So let's see. We know 0 has to be equal to 2t minus 4. And we can rearrange that whole equation and get 4 is equal to 2t, or 2 is equal to t. You know algebra. Basically, the point of t is equal to 2, we're going to have no horizontal change, no vertical change, that is, no vertical slope, and we're going to have a straight horizontal tangent line. So now we're just going to plug into our equations in order to get our x and our y. So we're given x is equal to t plus 5, where we found our t, the time at which we have a horizontal tangent line. X is equal to 2 plus 5. We can just substitute this in. It's lovely. It's great. We're going to get our x is equal to 7. We're going to plug into our y equation of y is equal to t squared minus 4t. You see I've just plugged in. We're going to y is equal to 4 minus 8, which is equal to negative 4. So let's see if we've actually done this correctly. We should get our x point is 4, our x point is 7, that is, Our y point is -4. Great job. And there is no vertical thing. Now, if we want to figure out why there is no vertical, I mean, we could just super quickly, let's give this a shot anyways. Okay, if we wanted to find where our vertical tangent is, we'd solve for when there's no. Oh, you can't even see what I'm doing here. That's cool. If we wanted to figure out, we really want to know where there's a vertical asymptote, we'd take the derivative of x with respect to time and find where it is equal to 0. So let's try to do that. We're going to take x equals t plus 5, and we're going to take the derivative of it. Cool. dx over dt is equal to 1. And what we realize is that's just never going to equal 0. So we know since the x, there's always at least some change in x for the slope, right? That there's just never going to be a completely vertical tangent line. And you're just going to write that that's not applicable. We're going to move on. We're going to do this. I am going to choose to skip 4b because it's basically the exact same thing as we did before. You all know my phone number and my Instagram. You can just spam text me in our worst case scenario. But I will move on to, I will do 4c because I do think it is kind of obnoxiously annoying to do. And I'm going to, let's see. Let's start, this problem wants us to know what the horizontal tangent is. So d. At a t value that is greater than pi. Awesome. And I'm also going to quickly rewrite some of the things that we've covered today. Let's see, that dy over dt over dx over dt is equal to our slope. And that a horizontal tangent line happens when dy over dt is equal to 0. And a vertical tangent line, I really hope you guys can read this, happens at dx over dt is equal to 0. So there's our little chart that we've got. And hopefully, actually, now that I've written these next to each other, it makes sense that when dy over dt is equal to 0, you've got a slope of 0, which is a horizontal tangent. When dx is over dt is equal to 0, you've got an undefined slope, and undefined slopes are vertical. Okay, awesome, super great. Let's solve this thing. Okay, so they want us to know the point of the horizontal tangent. So we're going to take this equation dy over dt is equal to 0. In order to do that, we got to find the derivative of y. And y is equal to -1 plus 4 sine of t. So let's take the derivative of this. It's going to be the derivative of sine and cosine. So this is going to be 4 cosine of t, right? And we're going to find when cosine of t is equal to 0. Now, we're going to look at our best friend, the unit circle. We can sort of just eyeball this and realize that our cosine is 0, or our x value is 0, at the points pi over 2 and 3 pi over 2, right? So both of these values would work, but since we restrict our domain, we're going to have to go with t is equal to 3 pi over 2. Or our slope is equal to 0 when cosine is 0. So our slope is 0, or slope of y is 0 at 3 pi over 2. Super great, super awesome, but that hasn't given us just the points. So we're going to do that whole thing. We're going to substitute back into the original problems that we got. X is equal to 3 plus 2 cosine of t. Substituting 3 pi over 2 in for cosine. And then y is equal to negative 1 plus 4 of sine of 3 pi over 2. Right? You're going to do some mental math, right? Or you're going to do math on paper. Listen, again, I'm not a cop. I'm not going to control what you do. But you'll eventually realize that cosine of this value is equal to 0. So x just ends up being 3. And this is negative 1 plus 4 of this value. And at 3 pi over 2, sine is equal to negative 1. So you get negative 1 minus 4. You get negative 5 as your y value. And I'm going to pretend I didn't type that. Wow, I wonder what this thing is. It looks like the point of this horizontal tangent, or the point when our derivative of y with respect to t is 0, it's going to be 3 equals 3 comma negative 5. Guys, I think we might be so fantastic and actually super amazing at this. Cool, awesome. And remember that if we want to find the vertical, we're just going to do the same thing, but we're going to start with the x equation instead of the y. Let's move on. Okay. This arc length is kind of annoying. You've kind of just got to memorize the equation, but at the same time, I think the equation is actually pretty intuitive, right? The equation here is we're going to take the integral from 0 to, let's see, t of the square root of dx over dt squared plus dy over dt squared. I think you're obviously going to multiply that by tt, as we all do with all integrals. And I'm going to double check my equation. Oh, technically you should write b and a for these bounds of the integral here, but doesn't really matter. They're generally going to tell you to start at 0, but sometimes they'll tell you a and b will be different values. Now, what we realize here, besides the fact that this looks really terribly ugly, and it will look much uglier later, is that this looks a whole lot like the Pythagorean theorem. And that part actually makes sense, right? So if we look at a curve, like I'm going to draw over here, and we want to figure out what's the length from this point to this point, right? We could actually take the change in x, this is the change in x, squared, plus the change of y squared, and we can plug that into the Pythagorean theorem to get this right here. And as we're going to keep on using, as with integrals, we're going to take infinitely small dt's, right? We're going to have infinitely small distances. So then we're going to get little tiny triangles that look like this, right? That are going to follow this equation here to get this length. And eventually, with infinitely small triangles or Pythagorean theorems, we're going to basically be able to calculate the length of this thing, right? By just calculating the hypotenuse of those triangles over and over and over and over and over again. All right, and that's where we get this equation from. It's a concept that this is the equation for, let's see, the length of a triangle, hypotenuse of a triangle, and we're just going to do that an infinite amount of times over these really small intervals until we finally sum up to what the actual length is. So I'm going to write arc length, so we remember that. And then I'm going to check my camera again and really hope that you can see this once again another time. And it looks like you can. Wow. Looks like I'm so great at doing this whole math thing, guys. And I think we should all be super proud and maybe donate a couple $100. In the meantime, though, we got this formula. Okay, let's try actually using it. So we're going to try with this A. Let's see. We get x is equal to t squared. I'm going to write that we're doing round 5 here, by the way. X is equal to t squared, y is equal to t cubed. We're going to take these equations, we're going to take the derivatives of them. With just some basic power rule. And then we're going to just plop those into our equation. From 0 to 2, because those are the bounds they give you, we're going to take the square root of 2t squared plus. Because these two are our equations for what x over dt, dy over tr. We're going to put that all in an integral, cap it off with dt. And let's do a little bit of simplifying work. Let's see. We could get 4t squared plus 9t to the 4th. We're going to square root both of those. And we should figure out that we have the equation. I'm going to plug this in real quick. This is a point in the video where the ripping eyeballs out part comes imminent. Okay guys, I'm done being emo. Done with the eyeball ripping out part of this segment. This is just going to be a really annoying integral problem, and that's why I'm not going to do the rest of these, and you can just text me or DM me on Instagram if you have issues. So we're going to factor out t squared out of these, because we recognize that, you know, that's the thing that we can do. 4 plus 9t squared. Right, and when we factor this out, we're going to start rewriting over here again. That's the same thing as the integral from 2 to 0. Cool, got this. Awesome, super great. And now we're gonna have to do everyone's favorite thing, which equals u substitution. Okay, so we're just gonna u sub in. U is equal to 4 plus 9t squared. U is equal to 18t times tx. I am honestly just going to skip through the entire u subbing process, and I'll just leave my work here and you guys can figure out how. So, we're so back and all that. Basically, what you're going to end up doing here is every single thing that I just did with the u substitution, but you are not going to forget to check your bounds. Don't forget to check your bounds. That's a really big, dumb, stupid thing to do. Don't forget to check your bounds. Okay, so you're gonna resubstitute in 40 and 4 for your bounds after you know, plug them into this equation here. But once you've done the whole thing with checking bounds and all, you're gonna get that your answer is like around like 9.073 once you plug into your calculator. So, demonstrated, as long as you check your bounds, this is how you do arc length. It's a whole integral. Let's see. I'm skipping the next two parts of that. I'm sorry, y'all. I'm sure we can, let's check if the order is right here. It is, let's see. But all we're gonna do now, we're gonna find the velocity vector given the position vector. And this really is not too bad. I'm gonna write 6a here because we're moving on. Not too bad, right? We're just gonna take, we know the derivative of position is going to be velocity. So let's see, our x right now is equal to t sine of t. You know, that's what they're telling you with this whole notation they've got here. Let me just write this out. What they're telling you with this whole notation here, it's kind of like, well, we're just going to think about it like this is your, yeah, this is your position. This is how you would calculate x given t, and this is how you calculate y given t. It's just x and y, and then you can find the derivatives in order to get the velocity vector. And these greater than, less than symbols are just part of the notation of how we do that. In this problem, I'm not even really going to write this out. We're just going to chain rule here, guys. We know how to chain rule. Super proud of all you guys for the fact that we know how to chain rule. We're just going to do chain rule in order to get what 6a and 6b are, which is going to be this guy right here. Awesome. Great. Cool. Guys, I was initially thinking about doing this for all you, but I'm realizing now that you guys just don't matter enough to me to do the rest of these. DM me on Instagram. You know what? So guys, I've been sitting here contemplating doing the rest of these. We get the point here. So guys, I've spent like a minute looking through the rest of these. We get the point here. We're just going to take the derivative of the x component to get the velocity with regards to x. We're going to take the derivative of the y position component in order to get the velocity with of the y component. And I'll give you the answers if you want. No, maybe you're using this to scam Miss Baggeson out of her money. But that's the same thing we're going to do on 6b and 6c. This is just an overview. Let's go into the super fun world of 7a, if we can read the instructions. This is kind of like velocity PVA, what we did before, position, velocity, acceleration, you know. We are going to find the position of a particle when we're given the velocity. So we switch from being given the position to be given the velocity. Let's start doing it. Okay. 7a. We're given that t plus 1 minus 1 is equal to dx over dt. I'm just going to write that first. Cool. That's our dx over dt. That's our dy over dt. Those two things are given. Remember, they're giving us velocity. So what we're going to take here, we want the equation not for dx over dt, but just for x. Not for dy over t, but just for y. And in order to do that, we are just going to take the integrals in order to get those equations. So this is just going to be a u sub, where u is equal to t plus 1, right? This is going to turn into the integral of 1 over u. And it's going to be ln of t plus 1. Now this side over here is also going to be a u sub. Isn't life great like that? U is going to be t plus 2, and we're just going to use basic power rule of integrals to get u. Cool. We're going to get that these are going to be our equations at x and at y. Now, so remember that this is still an integral, right? So an integral we need to evaluate at b and a, right? And in this case, our b and a are going to be the time that the position starts moving, or the time that the object starts moving, and the time that the object stops moving. So in this case, they're so lovely, and they give these to us. It's 0 and 3, and we can also write 0 and 3 on all the integrals here, and you would do that if you were a good calculus student. Right? So we're going to write 0 and 3 in all of these, right? In order to get that, and we're going to solve this. Over here, it's gonna turn into ln of 3 plus 1 minus ln of 0 plus 1. And over here, our y is gonna work out to being negative, 3 plus 2 to the power of negative 1 plus 0 plus 2 to the power of negative 1. And guys, it's a Sunday afternoon. You guys know how to type this into your calculator. I've typed this into my calculator before. All right, we get those things. The one thing that we have to keep into account though is when we take the integral of velocity, we only figure out how much we have moved so far. So we also need to add on our initial starting positions to this whole equation that we've got so far. So in this case, and they'll always give you these initial starting positions, because if not, you only know how much you've moved, right? So in this place at x, our x started at being 3, our y started at being negative 2, so we're gonna add, or I guess subtract this one to both of those. And we are going to get, you should get around 4.386 and negative 1.7 for those two components there. And you've just done a super great and lovely, fantastic job. Guys, this video is 55 minutes. Let's see what the people want. I think from here, we're just testing your ability to take an integral. So I'm going to leave you guys to do 7b and 7c. I've left you guys the answers on this board. I'm going to eat lunch after this. In the meantime, okay, here's some things that I think you guys should actually practice. Some things, practice everything on here. But here's something, questions that are kind of wild cards that we're going to explain how to do. We want to find the speed of a particle that moves with position vector secant pi t and tangent of y t. Tangent of pi t, that is. right? 8a. We're going to do, what here we're going to do is kind of like the arc length formula. We're going to do the Pythagorean theorem. And what that's going to be, I'm going to write it over here actually, is dx over dt squared plus dy over dt squared square root of that whole thing. So this equation here, not sure if we covered this in class, but this should kind of intuitively make sense to us, right? So what we're seeing here, if I can rub my eyes enough, Christ, but what we are seeing here is kind of the same thing that we're doing here. So your average or your overall, or at a certain moment in time, your speed in the x direction, and then you take your speed in the y direction. Let's say, or this is how much you travel in the y direction. This is how much you travel in the x direction. Your total should be what ends up being your length of this plus the length of this, both squared. So we can use the Pythagorean theorem to figure out the speed needed, what our overall speed is. If we just look at both sides of this triangle as how much we're moving x direction this way, how much we're moving y direction this way. Word vomit, but this video is going out to a whole entire 4 of you, so we'll be okay. So I am just going to, let's see, actually, you know what, we'll do this. We'll plug into, we're just going to plug into this equation. Let's figure out the derivative of secant. So I've written out the whole equation here of what we're going to do, and honestly, you guys, I just want you all to type this into your calculator. You're going to type this into your calculator, and you're going to get just around the speed. It's going to be around 2. Should be around 8.886. Oh, that's lovely. Yeah, honestly, guys, you could do so much, but just plug in this and put it into a calculator. Nobody wants you to compute secant by hand 4 times consecutively. You know, give yourself a break. Okay, now that we've got that figured out, okay, for everyone who wants to type it into the calculator, everyone got it right! Yay, I'm so proud of you guys. In the meantime, though, we're going to move on to A to B, because we're so close to wrapping this up. Okay, we are going to choose just to do one more equation today because we're at the eyeball ripping out point for everyone involved. I've been recording for over an hour. I have yet to ingest a meal. But we're going to go over 8b. I'm going to tell you how to do 8c, and then we're all going to circle back in a circle of loving helpfulness. So, we're given that a particle moves in the plane so that its position at any time from 0 to 2 pi is given by sine of t cosine 2t. But that's the position in component 4. So for what values of t is the particle at rest? This is a simple problem. This is kind of like our horizontal and vertical tangent line problems from before, and we'll explain why. We want to find, before we wanted to find, and I'm going to carve out a little box here, we wanted to find when dx over dt is equal to 0, meaning like there's no change horizontally, there's only a change vertically, and we want to find when dy over dt is equal to 0, right? We wanted to find when there was no change vertically and we had a horizontal tangent line. Now what we realize is if there's no change in either of these, right, there's no vertical movement, there's no horizontal movement, the particle is just at rest. So we're just going to solve for dx over dt and dy over dt. We're just going to figure out when both of them are at rest. So we're given this whole position thing, our position x of x equals sine of t, and our position of y is equal to cosine of 2t, right? So sine of t, x is equal to sine of t, our derivative, dx over dt, is going to be equal to cosine. Derivative of sine is cosine, guys. We're finally getting back to happiness again. Meantime, dy over dt is equal to 2 times negative sine of 2t. Cool. These should make sense to us. We want to find out when cosine of t and when sine of 2t are both equal to 0. So it can't just be when one is equal to 0. We need to go through both of them and figure out when they're equal to 0. Let's use like our best friend, the unit circle again. Oh my god, unit circle. You look so great, by the way. Cosine of t is going to be equal to 0 at these points pi over 2 and 3 pi over 2. Now, in the meantime, let's see, sine of t is going to be equal to 0 at the points pi and at the points 2 pi, right? So when this whole thing is equal to pi, it's going to be at the points pi over 2, and it's also going to be at the point pi. When t is equal to pi, then this whole thing is going to be equal to 0. So at pi over 2, at pi, and at 3 pi over 2, those are all within the interval, and those all make sine of 2t equal to 0. So we see that there are two overlapping points. Wow, it's just like what we want. We're going to test those. We're going to check our answer here. Okay, moment of truth. Okay, moment of truth. We did a super great job. And again, I want you to recognize the slope or the rate of change of dx and dy, they both have to be 0. Otherwise, like let's look at this point pi, right? At the point pi, it may be that dy over dt is 0, so there's no movement up and down, but there's still movement in the x direction. So in that case, we have to know that at that point in time, there's just going to be a horizontal tangent. But at these values where a rate of change of both x and y are equal to 0, that just means there's no movement whatsoever. We can almost think of it as our velocity vector at that point is going to be equal to 0, comma 0. There we are, guys. I'm going to explain to you how to do 8C, and then we're going to wrap it up. I'm going to figure out how to line up these videos, and we're going to put everything together. AC, all they want you to use is once again this arc length formula. They're giving you these equations for position, right? And they're telling you that the dot is somewhere in the plane. They just want you to find the distance traveled from. They're telling you the dot is somewhere in the plane. They want you to find the distance traveled when like t is equal to one value, like let's say t is equal to 0 here, and then the other value like t is equal to 1, which might be, for example, here. That's just going to work out to be arc length. And with that being said, wow, it looks like, guys, we did actually complete that problem after all, 2.430. With that being said, it's 2:32 p.m. and I am going to go eat a meal and finish my overpriced boba tea. Good luck with calculus, everyone. Good luck in the horse race that is human life. Good luck in the horse race that is calculus. We're doing great. Okay, see y'all Monday.